Thank you very much, Manila. Well, may I first of all say a big thank you to the organizers for hosting us here, organizing this event in this wonderful place at this venue. Yes, we're continuing with transport-related topics, and today I'm talking about evaluating urban traffic congestion, using OpenStreetMap and Sparse public transport data. I guess if it was transport conference, the order of these things would have been different. First of all, I would like to say that there is a paper that that represents a review of this work, which has been published in a couple of peer-reviewed papers in IEEE Intelligent Transport Conferences. One invited paper in lecture notes in computer science, and this paper will be accessible perhaps on the website of the conference. Okay. This is a joint work with Richard Gibbons, David Evans, Alistair Beresford, Jean Bacon, and Ken Moody. All these people are at the computer lab in Cambridge, and Adrian Friday, who is from Lancaster University. All right, so in 2009-2010, we had, well, I joined a project in which we had access to bus GPS data from Cambridge and area of Cambridgeshire, a county in England. And the idea was basically to use the data we had access to and treat buses as particles in the whole floor in order to say something about the whole traffic. Well, the bus data we had were sampled at a rate which, well, can be considered to be not high enough. Therefore, we call this data sparse data. Just in a minute, I'll describe the data we had, and also the supplementary additional data we used from OpenStreetMap, actually to say something meaningful about traffic and congestion. The immediate obstacle we see here is that if we want to use buses as bus probes, buses live in the traffic, but possibly between bus stops, or if they're not using bus lanes. So, in other words, buses can use roads in a specific way. Traffic lights can favor buses, can prioritize them, and so forth. So we would like to still having access to this data, being able to use it to generalize things to the whole traffic, using this knowledge that buses have specific behavior. Yeah. So I'll describe the data, and I'll show what we did with data to analyze journeys, journey durations. So I'll represent the variability analysis of journey times and also influence of contextual factors. And then I'll go to road traffic and congestion analysis. So the bus locations were recorded using GPS at the rate of once every 20-30 seconds, more rarely once a minute, once every 2 minutes. There are silence periods in the database. So these are due to various reasons, technical reasons, weather, and so forth. The data were obtained from the largest local bus company. And the data obviously needed some parsing and cleaning. So we used the road network, obviously, for snapping and map matching in this analysis, and we used it from the OSM, but what's more, we used additional information about road and infrastructure, positions of traffic lights, bus lanes, bollards or barriers that might only give access to buses or taxis. And the whole idea here is that, okay, as long as you know that this part of the road is used by buses in a specific way, you can subtract that behavior and do the rest for the whole traffic. And I'll show how we do that. We also used, because the data is sparse and we didn't have information about which route a particular bus was being taken, we had a difficulty at first even in extracting journeys. So for example, you have a route of interest and you have the whole data set of GPS traces. What we did have, so the traces are vehicle ID number and sequence of locations and timestamps. But still, if you want to extract a journey made by a bus along the route of interest, it is data mining a little challenge. So we found that we can use a technique which we call bus stop gates to extract journeys and then perform journey time analysis. We also used description of bus routes from either timetables of the local operator or again from OSM. Okay, and we also used a GPS tracker for validating the analysis we're doing here. So to collect basically high-resolution tracks. On this map, you can see the grayscale background is OSM image of Cambridge, and this shows the bus coverage of Cambridge, just snapping off data from 150 buses. You can see the coverage is generally good, and that's the advantage of using bus data. Often the fleets are, you see the infrastructure quite often is already in place, and this favors this usage and your research because static infrastructure. So to get more accurate information by instrumenting the whole city by static sensors might be prohibitively expensive for the local authorities, for researchers. Another advantage is that buses span the city throughout the day, in early morning hours, late evening hours. That is when information about congestion and traffic is of most interest. Now, just as an example of how a trace might look like, you can see red crosses here. You can see a cloud of points over there. What do you think it is? Exactly, the point. Yes, indeed. And here you can see two green paths, two green routes. So we'll concentrate on a case study, and I will use data from this arterial road to the west of Cambridge, which is Maidingley Road, and Histon Road, which is vertical in the northern part of the city. Also by the red cross you see a place of an accident on notoriously famous A14 highway, people who are from Britain would know what I mean. So there are often traffic jams there and accidents that, whatever they happen, to just bring the whole city and the highway to the standstill. So we'll use a case study one day when a lorry fire happened there, and we'll see the consequences on the traffic all across the city. Okay? All right, so on this slide you can see the schematic representation of Maidingley Road, and just places to remember. Maybe the city center is to the east of this road. Maidingley Road park and ride facility is 2.5 kilometers to the west of the center along this road. Okay, and in the upper plots you can see the dots. The red dots are sampling points, and we'll look at the bus positions in the space of distance traveled and time of day. So the upper figure, and you would have to believe me, this is a typical behavior that you can see for this particular road in Cambridge. Yes, and the lines are just connections of these dots. Yeah, so the raw data are dots, and the lines are linear representations. So what you can see there already is that between 7:40 and well, 20 to 9, you can see that the slope changes. Moreover, the progression of this increase of the slope also moves along the road. It just indicates that congestion starts from the center and moves in the opposite direction of where the vehicle moves. So you can see waves here. And this is a typical behavior. Then the traffic comes to normal afterwards. And you can see 22nd of June 2010, so the previous was a week earlier, Tuesday. On the 22nd of June, well, something different happened. After 20 past 9, there is no back to normal condition. There's actually worsening condition. No, 2 points to make here. So something has happened on this day. You might already guess it was that accident that I mentioned. Also, still this kind of data, we treat them as sparse data in the sense that, well, you don't really have detailed information of what was happening between the sampling points, right? Silence period might occur and sampling rate is not high enough, but we're actually able to restore that behavior. So to make that information more accurate and use it in evaluating congestion. Now, towards the city center, so 2.5 kilometers, so you can see clusters of points there, so that corresponds to the park and ride facility, right? So buses samples there more because they spend more time there. Yeah. And 0 corresponds to the point of making the road close to the city center. Okay. Now, I will show how we do the journey extraction. First, when we got hold of this database and we wanted to analyze simply just journey times that buses experienced or bus users experienced, passengers, we thought, okay, how to extract these journeys along the route of interest from this database. And we first thought of bounding boxes, bounding rectangles, but that procedure worked, it was not robust enough, was not flexible, and it was difficult to automate. And then we came up with this very simple idea of, okay, well, you can choose some points on your route and then create perpendicular segments to the route of interest and then just look at the sequence of segments between consecutive sampling points and reduce it to the regular expression problem, and then quickly extract all the journeys you need. More to this, you can actually estimate to make an adjustment for the intersection of these bus gates and more accurately estimate the duration of journey. Yeah, because sampling points that regular points or multiples of the sampling period of time. Yeah, so the journey from A to B, and there might be more bus stops with additional bus stop gates on the way. It's just the journey, the time needed to go from the first sampling point before crossing the first bus stop until the last, before crossing the last, minus time estimated, subtracted for these going along these segments. Okay. Then the analysis of journey times. See, I'm running out of time. I'll try to be quick because the ultimate goal is just to get 2 nice figures. But you need to do all this analysis. So this is a route of interest, and in this case, I just identified a set of bus stops, bus stop gates. They all happen to have south bearing of south. So we extract journeys, and here you have the analysis. We'll just export the analysis of journey times, and it's a single extracted data set of journeys corresponding to that route, and you can apply such exploratory statistical methods as box and whisker plots or quantile regression line in order to analyze variability of duration of journeys. Moreover, you can see that such contextual factors as whether the journey were made during the school term times, so outside school term times, affect the journey duration a lot. and statistical variability of it. So you can see an example here. All right, and then back to the idea of using buses as bus probes to say something about traffic and congestion. So imagine you extracted a bus journey, a sequence of sampling points, and then in the space of distance traveled versus time of day, red crosses are sampling points, then you can do linear representation of the journey, but you can do more. You can, for example, interpolate it using some smooth curves, and that's what we do using monotonic spline interpolation, and that gives you an immediate formula for restoring speeds. So on this plot, you can see the thin gray line is actually high resolution speed, which I recorded being on that bus. And by the thick line, you can, so the smooth version of that speed, of the velocity of the bus, is represented. And that is derived from interpolating these sampling points by the monotonic spline. And we also use the concept of local time, which is related to this function, to better see where, due to what reasons, buses were slowing down or speeding up. So the details of this, and this is the ABC of our methodology, the details can be found in the paper that was submitted. So once the velocity, the accurate information on the velocity is restored, and information about how buses use the road network is taken into account, we use the velocity field approach to map this information and summarize it and map it back to the road network and color it as, for example, Google do for arterial roads or for highways. And here you see two maps colored, so the road segments, and we use the natural road segmentation from the OSM data. And you can see, of course, you know, velocity field is a mathematical structure. You can compare velocity fields, but here, just exploratory analysis, and you could see that on the day of 22nd of June, I don't see the labels, but it's to the right, and the scale is corresponds to the average velocity corresponding to the road network segments. So you can see that congestion is much higher, and this is for 10 a.m., the what if I happened early in the morning, and this is a typical behavior. This is, of course, can be produced in a dynamic way, and one of the colleagues of mine is working now on actually dynamic representation, taking into account real-time feed of the data. And a related plot, and this is the last plot I'll show you, is actually travel time. We were very much inspired by heat map travel times produced by My Society, non-profit foundation in the UK. But what they did, they produced similar heat map plots for the data taken from the bus timetables. But those are static. And as you saw from the journey time analysis, journey times vary depending on the time of the day, time of year, and so on. This heat map is made based on the real-time data, based on the concept of the velocity field, and corresponds to what you could expect. How long would your journey take from, say, each point on the map to the darkest blue point in the center? And that is based on time-dependent road network weight road network, based on the velocity field, okay? You can see that journey from here to the center would have taken 60 minutes on the day of the accident. Normally, on a normal day, it would have taken only 20-25 minutes. Okay, so just to summarize quickly, 25 minutes. Probably no questions, all the questions afterwards, so from the paper. Just to summarize quickly. So we believe that the techniques we developed are effective. They deal with sparse public transport data. Public transport data become increasingly available, and you can use them complemented by all the additional information you need is actually available in the OpenStreetMap database. So we use road network, we use information about bus stops, locations, and also we need bearings. And regardless on whether